All right, so yesterday we finished up talking about solvent selection for acid-base reactions. We said that solvent is usually inert. You don't want it to participate. So the first example I gave you, we had the acid that I've got on the far left-hand side. I've got the base, which is NH2 minus. And then for this one, I picked water as a solvent. But we said water is problematic because it's actually more acidic than the thing we're trying to deprotonate. So instead of getting these ones are not observed. Instead of seeing that, you get deprotonation of your solvent instead. And that's usually not a desirable thing, so I'll just put a frowny face here. All right, so now the question is, what would be a more appropriate solvent? Should it have a higher or lower pKa? Higher. So usually we want a solvent with a higher pKa. And I'll show you guys a cool trick that chemists often use. Well, first you can go to this table. Okay, so for example, for this one, I'm going to use acetylene. And same base as before, I'm going to have sodium amide, which is NH2. So I'm going to label this as my acid. I'm going to label this as my base. And then for my solvent, I'm going to pick ammonia. Let me color code this. Base. And then solvent. Let's try to complete the arrow pushing for this. So do I want to draw my arrows going like that? No. You always want arrows to start at pi bonds or lone pairs. So I'll do that, and now what? Break the sigma bond. So now that sigma bond is going to be a lone pair on that carbon. Oops. All right, now if we think about our base, what's the base going to turn into? Yeah, the base is going to be another equivalent of your solvent, right? So in this case, our conjugate acid is the same as our solvent. This is really convenient because we have less to clean up at the end of the reaction, right? We don't have to get rid of some sort of salt. Instead, it's actually just become the bulk solution itself. So chemists oftentimes use a base where the conjugate acid is the same as the solvent. And I'll just abbreviate conjugate acid. So you may occasionally see this. It's not always the case, but it's often the case that you do this, which is why hydroxides, a really common base, is the conjugate acid's water. Water is a really cheap and plentiful solvent to use in chemical reactions. Solvents, you do have to be careful that your acid and base are soluble in them. If they're not soluble, then you're running into that oil-water interface, so you do have to also pay attention to solubility.
So let's say you can't find a solvent with the same conjugate acid, and you find something that you have a similar to value, or how do you decide?
That's a good question. So if you've got a base where the conjugate acid isn't a common solvent, then what you've got to do is just pick a solvent that has a higher pKa. We'll go into it more. Oftentimes with specific reactions, you want to be very careful with the solvent that you choose, but we haven't gotten into those reactions yet. Make sense? All right. So let's take a step back. And on Monday, we talked about two different theories. We said there was a Bronsted-Lowry definition. We've spent all 4 days talking about that. What was the other one, though? Lewis. So Lewis acid-base theory is actually a wider acid-base theory, and so the way I like to describe it is like this. All right, this is Lewis acid-base theory. It's a really big circle. Bronsted acid-base theory is just a little segment of Lewis acid-base theory. All right, so let's go back. Lewis said that acids do what? They don't donate protons, not in his theory. Do they give electrons, or do they accept electrons? It's a little bit weird, right? This always throws people, because Bronsted acids give protons, but acids accept electrons. So acids accept electrons. And bases donate electrons. In order for an acid to accept electrons, though, it has to have a place for those electrons to go. So quite often, they have some sort of empty orbital that can accept electrons in them. So do you guys remember one of the very early pods we looked at? We had that sp2 hybridized borane, and that had an empty p orbital. That was an example of a Lewis acid because it had an empty orbital that you could push electrons into. So let's try to link these two theories together a little bit. And I'm going to just draw a typical Bronsted-Lowry one first, and we'll compare it. All right, so if we think about our base here, in terms of arrow pushing, it's donating its electrons to the acid, right? So the base donates its electrons. That means that it must be a Lewis base, right? Because it's donating the electrons. On the other hand, the acid is accepting from the base, or I'll just write B with the lone pair. Therefore, it is also a Lewis acid. And then last but not least, we need to make sure that we break that sigma bond, right? So it's very similar, but instead of focusing on the movement of protons, we're focusing almost on that arrow pushing. Where are the electrons going? The base is the thing giving the electrons, so it's our Lewis base, where the acid is accepting the electrons from the base, so it's the Lewis acid. All right, so let's take a look at a common Lewis acid-base reaction. Okay, so for this one, I'm going to ask for your help on this. We've got NH3. I want you to draw the Lewis dot structure below with dashes and wedges if needed. So try to give it that three-dimensionality. And then same thing with BF3. And then we've got to determine what the products might look like. What's the shape going to be for NH3, for ammonia? Trigonal pyramidal, right? So I'm going to draw it on its side a little bit, and you'll see why in a second. And we've got these lone pairs coming off that nitrogen. What sort of lobe are those lone pairs going to be in? Well, first of all, what's the hybridization for that nitrogen? It's sp3, right? So these electrons are in an sp3 lobe, because that's the hybridization. We don't have any leftover p orbitals. Okay, so now we've got that Lewis dot structure. We know that this is trigonal pyramidal. All right, let's do the same thing with BF3. All right, what's the geometry going to be for BF3? Is it going to be tetrahedral? Is it going to be trigonal pyramidal? What do you guys think? Trigonal pyramidal, right? Okay. Trigonal pyramidal or planar? Planar. I think I said pyramidal on accident. All right, so this one we've got that. I'm trying to show it kind of flat into the board, so imagine those two fluorines, one's coming out at you, the other one's going in. All right, there's an empty orbital though somewhere. Because if you remember, this boron is sp2 hybridized. That means that there's a leftover p orbital. Okay, so let's imagine this p orbital sticking out like this, and this is an empty p orbital. But we know that the boron in this case is trigonal planar. All right, so you can imagine that empty p orbital is not very happy. Boron doesn't have an octet. It would prefer to gain electrons. So all that's going to happen in this reaction is these lone pairs are just going to get donated into that empty lobe on the boron, right? All right, so let's take a step back. Which ones are Lewis acid? Is it going to be the BF3 or NH3? BF3. It's accepting electrons. So Lewis acid, it accepts electrons, versus ammonia in this case is going to be our Lewis base because it donates electrons. Do you notice though in this problem I didn't move any protons around, so it is a unique reaction from a Bronsted-Lowry. All right, so now we can again draw this using equilibrium arrows. And then nitrogen is really going to stay about the same geometry. But now we're going to form a covalent bond over to boron. And then boron still has 3 fluorines coming off of it. So what hybridization will the boron take after it accepts electrons? It'll have to go sp3 because now it has a steric number 4, right? So for this one, it's a little bit strange, but it changes its hybridization from sp2 to sp3 because now it's got a new covalent bond to nitrogen. Oh, thank you. You guys keep me honest. So this adopts a sp3 hybridization. Another way of saying that is it is now tetrahedral. These can be considered reversible reactions in the same way as Bronsted-Lowry, so they can dock and undock with one another, but oftentimes the product side is so favorable, the reverse reaction doesn't occur to any meaningful degree.
So between those two, it's always a covalent bond. They technically don't give to take away.
Yeah, it's a little bit different than your traditional covalent bond because it is reversible, where a normal covalent bond we don't think of as being reversible. So what we normally call the product on the right is an adduct. And occasionally, instead of seeing a covalent bond as a single line, you may, in some textbooks, see it as an arrow, saying that this was where the electrons got donated from the nitrogen to the boron. But I think in the Klein textbook, he almost always shows it as just a traditional covalent bond like that. That's a good question. So this is referred to as our Lewis acid base adduct. I'll give you guys a couple of hints for spotting good Lewis acids, though. Good Lewis acids, I should say often, have an empty p orbital. So as you guys saw, boron as an example of an atom that often has an empty p orbital. What other atoms do you think might have empty p orbitals if they only have 3 other bonds?
Carbon. Wait, what did you say?
Yeah. Okay.
Nitrogen.
So boron with 3 bonds is a really good Lewis acid. You said carbon
Yeah.
with 3 bonds. Should that carbon have lone pairs on it? No, if it has lone pairs, it's an sp3, right? It doesn't have p orbitals. So it has 3 bonds, and what else? If it only has 3 bonds and no lone pairs, it's got to be charged, right? Is it positive or negative? Okay, with 3 bonds and a positive charge. That's a really, really good Lewis acid. All right, let's again focus on the periodic table. Right, what's right below boron? Aluminum. With 3 bonds. And oftentimes you'll see metals that are good Lewis acids, but in this class we're focusing on organic materials, not metallic compounds, so we're not really going to get into that in this course, but quite often metals are really good Lewis acids. Does that make sense? Yep.
So, for like, take for instance, the difference between carbon and boron, where carbon also has an incomplete octet, so it's like desperately looking for electrons. Would you say that for like a carbon that's leaning more towards a covalent bond, but a boron is more leaning towards just like a really strong polarization and attraction and less so of a covalent, or are they all just kind of?
Yeah, so your question was, if we're comparing boron that's neutral with 3 bonded atoms to carbon with 3 bonds but has a positive charge,
Right.
the carbon is absolutely desperate for electrons. So it's going to be an incredibly strong Lewis acid. When those electrons get donated to a positively charged carbon, that bond is really strong and doesn't want to give up those electrons again.
Basically,
So at that point, we treat it almost as a true covalent bond.
And boron is more just like.
Boron is a weird example. It really depends on what's attached to the boron. Sometimes boron's okay, being neutral and only having 3 things bonded to it. Other times it's incredibly unhappy. Yeah. All right, so let's make a little note too. All Bronsted acids are Lewis acids. Not all Lewis acids are Bronsted acids. This is confusing, right? We just saw an example where we weren't moving protons, but we said that that was a Lewis acid, but it's not a Bronsted acid in that example. However, all Bronsted acids are Lewis acids because they accept electrons from a base. So that's important to remember. You can classify every acid as a Lewis acid or base, but not all acids will be Bronsted acids or bases. That confuses a lot of students. All right, so let's go back and talk about arrow pushing just super quick, because again, this is another common mistake that people make. So like I said, the base is donating its electrons to our acid, and then the 2 electrons that were in this sigma bond are now going to hop over onto our acid. That gives atom A now a formal negative charge in this example. And then the base B now has a positive charge because it's sharing that lone pair with the proton now. So using Lewis theory, this is an electron acceptor. That means that it's a Lewis acid. Where this one is our electron donor, that means it's a Lewis base. All right, if we switch and we talk about Bronsted, this is our proton donor. That means it's going to be our Bronsted acid. Where this one is our proton acceptor, which means it's going to be our Bronsted base. Typically on quiz 3, when I go through and grade it, I spot at least a handful of quizzes where people have their arrows going the wrong direction. Please, please, please try to get those free points. Have your arrows going the right direction. It feels weird, but usually students get tempted to show the movement of the protons. We're more focused on movement of electrons as organic chemists, so don't show that purple arrow. Does that make sense? All right, so we have about 20 minutes to work on a short in-class activity. Hopefully you guys all picked it up from the front. If you've got that activity, what I recommend doing is work with a partner or push some tables together, and then in the last 5 minutes, we'll try to go over the answers pretty quick as a class.